have started that earlier. Okay, great. Okay, so in terms of generating primes, the student indicated your name is
Wang.
Wang indicated that he went about trying to generate these prime numbers in a stream in a similar fashion to what we used last time for Fibonacci. And those who may recall back to that may remember that we did something like this. Okay, so I'll just make the font size bigger here in large font. Okay, here we go. Boom. Okay. Can you folks read this? Yeah, and I guess this is still queued up for maintenance. So here's the thing we used to generate Fibonacci last time. Do you remember that? This is an example of what's called a co-recursive function. This is a function which takes as parameters some state, the kind of current state of where we're at in the Fibonacci sequence, A and B, these two successive values of it, and then uses that state information recursively by calling the same function with other arguments to generate a stream at the same time. So the stream generation is going on by appending items to the beginning of a stream whose next items are generated by recursive calls to Fibonacci. You see that? So we have Fibonacci as a method or function, you could say informally, and we are generating a stream through recursive calls to that, passing along the requisite state information needed to generate those successive elements of the stream. Remember that? Okay, so in terms of generating primes, what was the key challenge associated with that? What was a challenge that made it a little bit more textured than this one? That made it a worthy sort of thing to struggle with. It's not a trivial thing. What makes it more complicated than this? I'm not saying that you couldn't use an overall form like this, but what makes it more challenging? Yeah.
The complicated just going up dramatically, that is more trying to do that.
Okay, so there's more work with each successive prime. And why is that? That's true. There is more work. Why is it that there's more work? Because as the candidate primes, the potential, the numbers you're examining, whether or not they're a prime, get larger, what do we have to do with them? Well, how are you going to check if it's prime? What's our means of checking? Is this thing prime?
Divided by stuff.
Okay, yeah, so we check, is it evenly divided into? That's a horrible English expression. Is there any number less than it that evenly divides it? In particular, we don't need to look for any number less than it. We need to look, is it evenly divided by the what? By the previous primes. The primes, we don't have to look at all previous primes, just previous primes up to its square root, in fact. So take a number 35, right? We need to consider, okay, is that a prime number? And in order to do that, we would check, okay, can it be evenly divided by a set of previous primes? Can it be divided by 2? No. Can it be divided by 3? No. Can it be divided by 5? Yes, evenly. We don't actually have to go on to 7. Why not? Yeah, so it's more than the square root. If 7 went into it, it would only be because it's since it's greater than the square root of 35. It's only because the only way it could go into it evenly if it were multiplied by one or more primes less than the square root. So we need to filter the number. We need to sieve the number, according to a sieve of Eratosthenes, to sort of take a given candidate and check, is it divided by previous primes? And although the overall form of this might carry over, as one correctly noted, we have to do more work for those successive primes. And that requires us to maintain information about what? Here, the state we maintain is just two successive values of the Fibonacci sequence. For primes, what do we need to maintain information about?
The set of the previous primes.
Yeah, the set of the previous primes. We need to be checking each candidate prime against the set of previous primes. Okay, so I don't know how the methods you used. I'll show you two different methods that you can use to consider this. And the first of them, just as exactly as Wong noted, is one where we are using a co-recursive framework, and it mirrors the framework we use for Fibonacci. So here we have generate primes, and it takes in two things. It takes in a candidate and a list of primes, or a stream of primes thus far. Okay? Needing to be a string there. But the main point is it generates a string. Okay? So we start with some candidate for it. That's kind of our current place in the sequence. And this is kind of like A for Fibonacci. It's kind of where we are in the set of primes we're considering. And then we have to accumulate along the set of primes thus far so we can check them against each successive candidate. And this is going to generate a stream of lines. And what we're going to ask here is these primes that we've seen thus far, if we consider only those up to of such a value that their square is less than or equal to the candidate, up to the square root of the candidate, does there, amongst those, if we filter them down to that set that are less than or equal to the square root of the candidate, does there exist amongst those a one of them, at least one of them, that actually evenly divides this? And unfortunately, we're dealing with the strictures of the screen here. But we ask, okay, does there exist among those smaller primes, those ones less than or equal to the square root, a situation where it evenly divides the candidate number? In other words, we take the candidate modulo that, we get 0. If so, there's even one of those that goes evenly into it, like 5 goes evenly into 35, then we know that this candidate is or is not prime. It is not prime. It's a composite number. Okay? So in that case, we just go on to the next candidate. We don't have any more primes to add to the list that we've been maintaining. We haven't identified a new prime, so we don't need to append that to our list of primes we know about so far. We go and consider the next candidate. Okay? What we are going to generate for this call is going to be whatever we're going to generate for the next call. And we're going to go to the next candidate, and the next candidate, and the next candidate. Okay? This is what's called, by the way, a tail recursive function. Have you heard the term before? Tail recursion and 340 maybe? The reason it's tail recursive is what? What distinguishes it as the tail recursive? The fact that the return value of this guy, generate primes, of that call, is just exactly the same now as the candidate value of this. We're not doing anything after we call onto this. We're not like taking this value and adding one to it or appending it to something. We're just returning it. Now that may seem of dubious significance, but what it really comes down to is the Scala compiler and other compilers for similar languages can turn this into iteration instead of a recursive call. So it actually doesn't have to build up the stack. You might say, oh, it's calling this recursively. Maybe after 10,000 calls, it's going to bomb out because the stack is going to be filled up, and we'll get a stack overflow, and we'll get an error message. Well, it turns out it doesn't happen because this is a tail recursive call. We don't need to, in fact, build up the stack. It can turn it into recursion. It can turn it into a loop behind the scenes. Okay, so that's for the case where it's not prime. How if there exists for all primes which are less than or equal to the square root of the candidate, let's consider 37. Consider all primes less than or equal to the square root of 37. 2, 3, 5. Suppose there's none of them that they go evenly into this number 37. Is that candidate a prime or not? It's a prime. Nothing else than a square root that goes into it evenly. We've got ourselves one prime. We have found a prime. So here is an on-tail recursive call. Okay. We are going to generate the stream that we return is going to be whatever's returned by this candidate call, by this further recursive call, where we're considering the next candidate, 1 plus this guy. And we're going to tag this candidate onto the beginning. But not only do we have to tag it on there, where else do we have to tag it on? Where else does this candidate need to be considered? So this is one of the primes, so we're going to append it to all the primes that come from this. But where else do we need to tag it on? Well, we need to, remember, when we're calling generate primes, we're telling it all the primes. Oh my gosh, okay. We're telling it all the primes we've seen thus far, right? Primes thus far. So we've got to tag it on to those as well. So we pass it on, let any further testing take this prime into account. And that's it. That's it. So here we basically have two cases to consider. This case where none of the previous primes evenly divide this number, in which case this number is not a prime, and the primes that we're going to return from this are just going to be the primes any primes that we return from the next one. And this other case where this number is a prime, and so we've got to squirrel it away and remember it when testing further candidates and tag it on here. Do folks have some feel for how that works then? And why that works that way? Okay. Anyone want me to answer a question about this? This is not trivial. This is not trivial. That's why I asked you to struggle with it. Give it your darndest, not your damnedest. Don't spend all night on this. Okay? Number theory is not one of those things you can spend all night doing, and nor do I recommend it for this sort of programming. Okay, so here, having received that, we can generate primes, and I will go and engage in this. And why don't I just go post right now? Here we go. Boom. Why don't I just go post that solution in case any of you, oh my gosh, well, a nice idea crushed by an ugly fact. I guess my connection is not suitable. Okay, well, I won't do this, but here's generate primes. Let me do it in front of you. We actually don't need Scala.math. Previously, I'd computed the square root and done it that way, but I thought this way was a little bit slicker. So here we go. I'm going to go copy this in here. Hey, come on. Okay, let's engage in frobbing. Okay, boom. Okay, there we go. Paste, and I'm going to paste this in. Boom. Oh my gosh. Okay, value. Okay. Oh, yeah. I did some last minute tweaky of this. Okay, fine. So this is going to be v is a long, and we're going to return. Come on. we're going to return here something to indicate whether or not v times v is less than candidate. Okay, there we go. Good. There we go. Boom. Paste this in. Okay. Great. Okay, so now having done that, we could say primes equals generate primes. And now we have, why is it only listing this one? Where are my other primes? What's going on here? Remind me. Why is it we see this? Yes, streams are lazy. Streams are lazy. Are they by need lazy, or are they by name lazy? Yeah, they're by need. We compute it once. What's the difference between by name and by need? By name, if I ask for it again, what's going to happen? Compute it all again. By need, what is it going to do?
If we ask for the first 10 times, then if we come back to the first 10 times, it'll be done.
Yeah, they're memoized. They're remembered. You could think of they're memorized. It remembers them, so it doesn't have to compute them again. Now that is a trade-off. What's a positive side of that? We don't have to compute it again. What's the negative side of that?
Actually, a lot of mess things.
Yeah, it can keep around quite a bit of memory unless you're careful. Okay, so how would we get the first 10 of them? Good. Take 10 and what's that gonna give us? If we do that, why isn't that giving us it? Yeah, we have to force it. Now, there's actually a more flexible thing that I didn't introduce earlier. I don't want to overwhelm you with too many things, but you could do take while, okay, and you can say as long as it's less than 1,000. So here are all primes less than 1,000. Yeah, it's if we do this again, right? Let's go say primes now. What are we going to see? If I do primes, what am I going to see? Why am I seeing all these suddenly? Because they were memoized. Because they were remembered. They were calculated, and having calculated it, it remembers them. That take while is really useful, actually. It would have gotten us out of a pinch a few days ago when we were seeking to sort of find numbers in a certain range, and we tried to force the entire thing, and it didn't know that we had already found all of those between x and y, and so it kept on looking and kept on looking. Ladies and gentlemen, this take while is a very useful construct when you have ordered values. It just takes as long as that's true and then stops. Now, if it's not ordered, if they're in all sorts, if they were random numbers, this would offer only occasional use because it isn't so often that you say, okay, take while this is true, and then because the rest might be even larger or what have you. But here they're ordered, and so we might as well use this, right? Useful indeed. Okay, so let's continue to talk about primes, though. There's a more elegant solution yet. Yes.
Just making sure, it got memoized because he stored it into a value, right?
It got memoized because there was a yes in the sense that I had a reference to this stream, and the stream got explored, and as it got explored, each successive element, it memoizes that. If I hadn't put it into a value, if I hadn't associated a value with it, if I hadn't said this val primes equals that, then each time I call generate primes, it will generate a new stream, and here, I'll do this, right? I'll say, watch this. Okay, new stream dot take while this thing is less than 1,000, right? And we'll force it, right? There we are. If I do this again, do you think I'll see those? No, because it's a different stream. Each time it's generating a stream. And so it's not the same stream. That other one, it explored really well, but then I said I didn't keep it around. I didn't even have a reference to it. So it may have gotten garbage collected more or less immediately because I didn't have a reference to it anymore. But because I said val primes equals this, then those primes had a reference to them, and they're not going to be garbage collected. And every time I refer to prime subsequently, it's going to find them. Here's primes, because it's still pointing to that thing which got explored and which got memoized. Does that answer your question? Ladies and gentlemen, primes. Ladies and gentlemen, this code exhibits a modicum of sweetness by my aesthetics. It's fairly elegant in its depiction, but we can do better than that. I can't remember honestly where this next one came from, if that was something I came up with or one of my students came up with, but sweet it is. This is a prime stream here. This functionality uses an additional feature to exact incredible terseness from them. What's different from the above? What are some differences? So this is the definition here. This is a prime stream definition. What's the difference from the above? Give me an obvious thing that's missing here that was present above. Okay, this is a lot shorter. Yeah, let's move that down so you don't. So this is shorter. It's one line compared to this. But what else is different? Yeah, we're not defining a function here. There's no co-recursion going on explicitly where we're calling this thing, recursively like we did, just as Wong said, with Fibonacci. Right? We were calling this thing recursively. Here we're not. So what's going on here? What's taking the place of that recursion? There's something clever going on. Yes?
Well, it only evaluates as much as we need. It's a lazy function, so it can go on forever, essentially. If we say take all, it will literally keep going.
Yeah. Okay, so you'll notice this key attribute, lazy value this. What's the difference between a lazy one and this? Remember we saw it last time. What's distinct about lazy values? Yeah, they are by need. Excuse me. They are by need. Yes, that's correct. So if you use them multiple times, they're only computed once. Good. There's another feature that's different about lazy values and other values that we're using in a key way here. Let me try this, okay? Lazy. This is not going to be terribly meaningful, but humor me. Lazy val foo equals foo plus 1. Okay? Okay, this, you'll notice that here it's complaining. But it's complaining merely because of the missing type. Now, meanwhile, if I say val bar and equals bar plus 1, do you think it will allow it? Well, well, I'll be. Okay, well, you learn something new every day.
Does it init to 0 and just say it's 1?
Yeah, it apparently mumble. It apparently mumble. Yeah, it probably inits to 0 and mumble. Mumble. Okay. I gotta check this out. Okay. Okay. Baz equals. Okay. I've already defined bar. I've already defined foo. Okay. It's time for zap. Okay, okay, this is really interesting. So if we did that, it's going to say it's not found. So yes, it apparently, it must be doing it to 0. That's all I could think of.
You tried bar? Is it a bar?
Sorry?
Like we can bar, does,
Do bar here?
no, like var.
Oh, var.
Yeah, is it var?
Okay, well, a variable would be different, yeah. But here it does nothing other to call itself recursively. Okay, okay, that's an interesting message. Well, this will require some study in my office, but the basic deal here, ladies and gentlemen, is that this is using a similar trick, where this prime stream appears on the left. Yes, it's being defined, but where else does it appear? On the right. We're actually building up this stream as we're using it. So this prime stream equals to, appended to a stream that consists of, what does .from mean? Remember that?
Just the integers starting at 3.
Yeah, this is basically an infinite stream of ascending integers. Okay, it's not really infinite, but it's approximate. It's approximately infinite. It's a mathematician would shudder. It's really big, yeah, and we treat it as essentially infinite. And then with that sequence of rising integers, we filter to only keep those. We only retain those. We only select those, such that all the elements of stream prime, which are less than or equal to the square root of this number being considered, for none of them is it evenly divided by any of these previous primes. So it's a very similar logic. It's just this prime stream is being used as the list of the primes as it is being defined out from under us. Its earlier elements are being used, tested, to see if they evenly divide a candidate. I is this candidate here. And we're, from the ascending integers, just selecting those that pass this test. We're just selecting those from this ascending list of integers which are not evenly divided. In other words, for all of the previously identified primes, it does not divide them evenly. We're selecting out those integers, and those go into our prime stream. And so this builds up, and it builds up in this single line. So let's run this. Here we go. Here's a prime stream. Here's our prime stream. And let us now take 50 of these and force it. Right? There we go. There's our prime stream. Now, one slight difference you may notice between this and the above is the other generated a stream of longs. This one didn't, because this dot from works with integers, so just kept it as integers. Yeah?
So I was under the impression that streams were, like, in this case, would be inherently lazy, so why do you need the lazy keyword in front of it? What would happen if you ran it without it?
I think I tried that, and I think it did not work, but let's give it a try. Let's give it a try. So my wife has a PhD in biochemistry, in addition to being a doc, and prior to that, she got a PhD in biochemistry. And the word, hey, let's try it, is not something you utter in a biochemistry lab. I wonder what would happen if we combined these two chemicals. I think in our lab when I was at grad school one time, they had to evacuate because they had created phosgene gas or some poison gas that was used in World War I. So they had to clear out of the lab. So, anyway, it's one of the reasons she doesn't like to see me cook. Let's try it. She eloquates things very carefully. Okay, So, ladies and gentlemen, prime stream 2. Let's give that a call. Let's give that a try, and now we have to change this to prime stream 2. Ooh. Okay, let's now try this. Prime stream 2 dot take 50 dot force. Okay. Okay, so far so good. Sweet. Good man. Your name again? Alan, yes. Alan. Good man. Ladies and gentlemen, Alan has done this one thing better. Sweet. Yeah. Okay. I was thinking it's because only lazy things allow their use on both sides, but we already seem to have disproved that theory. So you learn two things every day, I guess. Anyway, nice thing. Nice definition. One line primes. Civic Eratosthenes, same basic algorithm as above, same flow intellectually for what's going. It just, we use the language and Stream's ability to be lazy, as Alan noted, to do it a little bit more elegantly yet. Does this strike you as kind of a nice thing? You can do that in one line? Or is it scary? Okay. Okay. Great. Okay. Anyway, streams, ladies and gentlemen, streams. Powerful, and they abstract away, ladies and gentlemen, from how much of the computation we need. They let us defer the decision how much to perform by allowing us to sort of declare it, carry it around as a potential computation, and then tap it when we need it. As we'll talk about later, this is an example of abstraction by deferral. It's sort of like currying allows us to defer the decision about what to use for later arguments until a later time, and allows us to get a lot of flexibility out of it. Okay, ladies and gentlemen, I'd like to now we have some extras. I didn't ask you to do this. I was afraid maybe the take-home exercise was a bit too cruel in terms of time taken, so I didn't want people to freak out about it. Here's a few extras though. Here's is prime. Let's do is prime here. All right. Is prime is going to basically ask, okay, given that we have a prime stream, we're going to check if basically there's any of the primes equal to n, where we consider only those up to less than or equal to n. Why do we need this take while thing here? How if we just said, does there exist one that equals n? Okay, but I would tell you that it's going to be computing them on demand. So if we keep on saying, give me the next, give me the next, give me the next, prime stream, being lazy, is going to be going and computing this while we demand each successive one. That's part of being lazy. It's going to be computing it along the way. So, but what's the problem? Why do we need to do this take while thing? Why can't we just say, does there exist one that equals n? It's an infinite loop. And why is it infinite?
It doesn't know that they continually get larger.
It doesn't know they continually get larger. Who said that? Good, Alan. Good man. Yeah, it doesn't know they continually get larger. It doesn't know to stop. So if we just said, among all the primes, does there exist one that equals n, it would just go on forever. So instead, we take advantage of the fact that we know they're rising. And so we'll only get those up to less than or equal to n, and consider, does that set include one that equals n? We can actually reverse this. We could do it all at once, and basically, we could check if there's one that exists. Well, no. I think that's pretty good. We might be able to optimize it a little bit. Anyway, this is prime. Do you yes? Warren.
Do we need to use that factor? Let's say that we had a stream of primes, but they're all completely randomized where they were. Can we just simply like iterate through the stream somehow and get it that way?
Yeah, but the problem is we could always eventually know, is it there? By going long enough, we could know if it is there, but we'll never know if it's not there, right? Because it might always just be one more, require one more yet for us to look. It could still be there. So that would transform a recursive problem into a recursively enumerable problem for those who are in the class on computability theory. There are certain types of questions we can answer yes or no, and then there's certain types of questions we can only know if it does halt, but we'll never know if it doesn't halt without running it arbitrarily long. We'll never know. If I ran it just a bit longer, would it halt? Right? Here's is prime. We can turn it into a problem that's decidable by actually doing this test. Okay, so is prime 37? True. Is prime 36? False. Prime 35, right? Is prime 237? False. Is prime, 8191? True. Is prime. Okay. Sweet. Now let's create a stream of Fibonacci's. Here's our Fibonacci's. You should be able to generate that definition for yourself now. And here we go. Here's our Fibonacci's. Let us create the prime fibs, right? How do I create the prime fibs? Okay, so here are the Fibonacci's. How would I create prime fibs?
Filter on is prime.
Yeah, Fibonacci's dot filter is prime of this. All right? Here are the prime fibs. The first of them is 2. Prime fibs dot take 5 dot force. Here's the first 5 prime Fibonacci's. Okay, now it's worth reflecting on what's going on here. There's some pretty sophisticated stuff happening. When are the Fibonacci's actually computed? As we need them. When are the primes computed? As we need them. And we need them here for what? To ask about is prime.
So the Fibonacci should be resolved up to 89, and the prime should be resolved up to around 89, right?
Good. Okay. So that's a great question, Warren. So let's sort of reset both of those back to their primal values, right? I think for is prime, I defined it in terms of prime stream. Here's prime stream. Oh, okay. So prime stream, I had only taken, I'd taken the first 50. Okay, so let's reset this back to its original state. Here we go. Prime stream. Here's prime stream. It's only defined up to there. Great. We will leave it in its primal state. No pun intended. Here we go. Here's is prime. Here are the Fibonacci's. We're going to redefine. We actually don't need to redefine the definition of the function just here. So here we're going to have Fibonacci's. Boom. We're going to have prime stream. And both of them are basically untrammeled. Okay? So now we're going to compute the prime fibs. Okay? Now let's look at the Fibonacci's. What should we see now? Why do we see that? Look, how about the prime fibs? What are we going to see now? Why are the Fibonacci's partly expanded here?
2 is the first prime.
Yeah, this is the first prime Fibonacci. Remember, it's filtering this. In order to show the first one, it has to start performing the computation to show us the first, right? Right? It's by need, ladies and gentlemen. We're saying, give me the filter. It wants to give us a stream. It wants to compute the first element of the stream. So it starts filtering through the Fibonacci's to find in search of the first prime. And it finds it at 2. And in the process of so doing, it is expanding the Fibonacci sequence and finding each, right? Right? So, how if we now ask for prime fibs dot take of, say 5, right? We're going to say force. It's 89. So now to Warren's question. I wanted to have a clean examination of it, a controlled experiment here. So we reset both of those earlier. Okay, what should Fibonacci's be, up to what should Fibonacci's be expanded? 89, I would conjecture, yeah. There we are, up to 89. These are the fibs up to 89. Notice that the prime fibs don't include all of them, right? Because there's ones in between here that are not prime, but had to get explored in order to find the first 5 prime ones, right? Get or not? Okay, ladies and gentlemen. So how about the primes? The prime stream. What would we see here? Up to 89 as well. Suppose we wanted one more. One more. For 6. Now it's up to 233. Okay, let's try the fibs. Here are fibs up to 233 and the prime stream up to 233. Ladies and gentlemen, these are being computed for us lazily behind the scenes. Let me put it another way, which will have significance in just a few minutes. These are being computed incrementally on an as-needed basis. Yes, it produced a stream, but that stream is being produced as we need each element. This computation is taking place over time as we need it, and it is taking place across multiple data structures as we need it. All because we're taking successive elements, ladies and gentlemen, of prime fibs. It is driving primes, the exploration of primes that is driving the exploration of Fibonacci's. Because we had asked for the Fibonacci's which satisfy is prime, and is prime uses the prime string. Comfortable with that? Yeah. Okay. Okay. So, an important point here, ladies and gentlemen. Okay, I want to drive home this point of incremental computation because it has great significance, okay? Okay, so I'm going to explore something here with you. I sent you a bit of code, maybe 20 minutes prior to class, something like that. And it would be handy in a few minutes if you had enjoyed recourse to that. I am actually, so I'm going to leave prime fibs and so on, and I'm going to make sure I'm in the right folder. Good, I'm in the data folder, whence my document will come. I am going to go take this thing here, which is basically a bit of code where we're going to take a stream from one and we're going to successively map things on it. So here, can anyone tell me, what does this do? So let me make the screen smaller. Okay, there we are. Okay. No, it doesn't seem like it is quite visible, but there it is. Yeah. Okay. Good. So what does that do? What is?
It does stuff to a list of like all possible integers, right? So like from 1 to
Okay.
infinite.
That's right.
And
And given those, what is it doing?
Squaring them.
Squaring them, and then it is
Getting all of them between 10,000 and 15,000.
good. And then what?
And it adds them all.
Adds them all up. Okay. So that's good. Ladies and gentlemen, I'd like to talk about how this computation takes place. Okay. And in order to make this particularly clear, what I'm going to do is, and I just want to be careful here because I did put this together. I'm going to do a take while I is less than 15,000 here. Okay, less than or equal to 15,000. I just want to make sure we don't run afoul of anything. Okay, oh, yeah, no wonder. There we go. Yeah, there we go. Okay. So here's the square A. Okay, square A. Okay, here we are. So this square A resulted from this computation, right? The first element is 0. Where did that 0 come from? Anyone remember? Well, what is this scan doing? This scan is adding up successive prefixes of these. Starting at 0, this is the initial offset, it's going to be adding each successive one on. So I'm going to do .take 5 .force here. Okay, here we are. Here's 10,000, and 20,201, 30,605, 41,214. So it's basically successively adding together these perfect squares from within that area. Okay, that lie between these values. So maybe I'll ask you this: given that, if I do take, oops, what am I doing? Here we are. Take 5. I do take 6. Okay, square A. Take 7. Okay. You'll notice it's not computing something more, but I could do force it, for example, force the first 7 of these. Where are these values coming from? Well, they're coming incrementally from each of these pieces, right? What is taking place? Well, this 63,000 is coming from adding together a set of elements here. And in order for it to produce this element, it needs to drive these earlier computations, right? So I'm asking it for the first 7 elements returned by this whole thing. And in order to compute those 7 elements, it is needing to get this filter done, to do this take while, to do this filter, to do this map, to do this from, so that it can generate the first 7 elements, right? Okay, watch this. So let's unpack this a little bit. Suppose I deleted this scan here. What would I see if I just did this? 10,000, okay? 10,000, it's 100 squared, right? Only that's computed here. If I went upstream of that, it would still be only 10,000 that's computed. If I go upstream of that, what will I expect to see here?
10,000.
Huh?
Or just 1.
1, right? How is it that we're getting this 10,000 here?
You're filtering on anything. greater
Yeah,
than
so
10.
so in order to get this value, what did it have to do? It went through 1, 2, 3, 4, 5. It was, for each of them, it was doing this map, creating this map. So 1 became, after the map became 1, 2 became 4, 3 became 9. It then tried to apply the filter. Have I got my number, my first number yet? Have I got the first number? Right? For 1, for 4, for 9, for 16, for 25, for 36, for 49. Right? It's doing this for each one in hopes that it will get the first number needed to list this out. But for each of those, it is being filtered out, is it not? It is being filtered out by this. So it still hasn't gotten its first number, right? Let's just make this very explicit. I'm going to call these guys these are horrible names. Val squares. Squares. Okay. Squares. There we go. Squares, ladies and gentlemen. Welcome to the squares. Okay, so now what I'm going to do is to make this all very explicit, I am going to go back to this. I should have planned this, but better Nate than never. I mean, better late than never. We're going to do squares here, right? Here are the squares. How many of these squares are computed here after I did it? Just this one, right? After I do this, how many will be computed?
Lots.
100.
There they are. They stand before us in regal beauty. So this is the first 100 or so, right? Okay. So, ladies and gentlemen, the squares have been forced to evaluation. Why have they been forced to so many to be evaluated? Because it kept on trying to get some that would pass this filter, so it could print out even the first of these values, right? Even the first of these values. It was doing that filter. And now if I wanted to do, a few more of these, if I wanted to do, let's say, the first 2 of these, okay, and I'm going to do force here, okay. So here, this 10,000, okay, I'll do the first 3. We'll get something greater than 10,000. 20,201. Okay. So how many of the squares do you think are computed now? Well, I'd had to compute up to, I think, this guy here. I'd have to think about this one. But evidently it did have to compute it. So it needed to compute more of those, right? In order to get the thing which passed this filter and to feed into this, to sum them up, to sum up these successive prefixes. This is just summing up the prefixes of successive ones. It needed to compute more, right? So it's performing this computation not all at once, but it's computing it, on a as needed basis. Do you appreciate that? Okay, let's drive this text now that I sent you. Let's take a look at this text that I sent you, and let's run it together. Okay, that's my preference. Let's run this thing together. Okay, here we go. I think I sent you this guy here. That's the last thing. So in order to run this text, we have to do Scala import scala.io. There we are. We need this for the so-called source, for it to read from a certain document. Okay? Now, I sent this to you as an array. Okay? Here we go. This is an array. And what this is doing is going and, well, you could tell me, what is this doing? We saw it before. This is part of the answer to a previous take-home exercise. What is this doing? Can anyone parse it?
This is grouping by the words or the lengths.
The lengths, yeah, the lengths of the word. Okay? And then it is computing how many of them there are. This is this map values. The values, after group by, what are the values consisting of?
Lengths paired with the numbers.
Yeah, all words that share the same length. And then this counts the number of such words. Okay? Group by groups, it has key and value. The key is going to be the length of the word, like it's foo, length 3. It's, A, length 1. It's, Scala, length 5, right? And then associated, after a group by, associated with that length, or associated with that key is what? A set of values, right? It's actually a collection of values, all the words that had that length. And so it's getting the size of that collection here, okay? Okay, but ladies and gentlemen, this is doing it as an array. So let's unpack this going back. This is as an array. So this last thing sorts them to be in order of ascending size. So I'm going to get rid of this sort. Here we are. Now it's no longer ascending sort. Okay? This is a full collection, though. Let's eliminate this 2 sequence. Now we have a map. Notice it's a full map. Do you get that? This is a full map at this stage of the pipeline, right? Do you see that? It's a full stage. Let's go back one level with the pipeline further. This group by, what are we going to see here? We're going to see just one value?
No, it's still full.
No, it's going to be a full thing here. Here are the list of all words which contain 5. And I think if we were to explore this further, we would find the worthy name of Scala in that list. Okay? Okay, let's go back one level yet. What is this going to be producing? Is this just going to be one value we're going to be seeing? No, it's a full collection, right? At this stage of the pipeline, it has a full collection, right? Full collection of all these words. Let's go back one level yet to this. What are we going to see here? Well, we're going to see basically a similar thing, but it's not going to be in lowercase. And now if we go back here, what are we going to see? It's going to be, again, a full collection. It's going to have lots of these little things of 0 length. And if we go back yet one further, we again are going to see a full collection of lines, right? So my point is, ladies and gentlemen, this pipeline is going to look very similar to the pipeline we will see in just a moment. But at each stage of this pipeline, we are seeing a full collection computed. Are we not? After this get lines to array, there's a full collection. After the flat map, there's a full collection. After the filter knot, there's a full collection. It is chunking forward in computing this, generating collection here. After this is done, it's generating a full collection. After this is done, it's a full collection created. After this map is done, it's a full collection. After that is done, it's a full collection. It keeps on creating these whole new collections along the way. Each of which, gotta avoid yelling this. Each of these collections occupies substantial memory. Creation of each of those collections is requiring gobs of memory, potentially, if you're operating on large data. And as soon as we collect it, as we go into the next stage, we're throwing away the earlier one. But we're keeping a lot of memory allocated at once because we're doing it for all the data items. This entire document has been processed to arrive at the collection here, right? The entire document to arrive at here. Now for this document, which was merely a master's thesis, that might only take a megabyte of memory, maybe a couple megabytes. But ladies and gentlemen, today's modern business environment, research environments, you might be dealing with tens of millions, hundreds of millions. And in your professional lifetime, yes, an order of magnitude or 2 orders of magnitude larger easily within a decade or two of data. And that's very expensive to keep all these data structures around. Keep on creating them, keep on creating them. And more to the point, we create them just to apply a simple operation to them. A further operation, like to turn it into lowercase. We're creating a whole new data structure. Got or not? Do you understand the concern there? Creating this whole data structure of strings. Now we create another whole data structure of strings to the lowercase version of it. Might seem to you a tad wasteful. Perhaps to some, even more than a tad. I'd like to change the text that we see here in a minor way. Changing it from to array, ladies and gentlemen, to a fateful 5-letter word.
Stream.
Indeed. Okay, here's the final component. I want to be clear here. Final component, at first blush, doesn't seem to be a lot different. What's going on here? Well, we get out an answer sorted with. Let's unpeel the onion. Let's step back. What led to this? So this is a sort. I'm going to go back to this 2 sequence, okay? Pretty similar, not too much difference right now. Here's our map. Map the values. Here's our group by. Now here we start to see something a little bit different. What's different about what we're seeing here?
The map values have not been computed yet.
These actually haven't been computed yet. They have yet to be defined. We found one 29 length set of characters, which
It's one that's 45 full of disease.
yeah. Let's focus on Dylan. So here it found Dylan, and it said, there's a 5. There's a thing of length 5, and it's waiting as to whether there's others. It may find others eventually. It hasn't done the full scan yet. But let's go back before group by, and this is when we'll start to see a big difference. Here, ladies and gentlemen, is we're at this part of the sequence. Why are we only seeing one thing here?
First word.
First word. The first word, which is non-zero length. Why aren't we seeing more than that? We haven't asked for them. We haven't needed them. Remember, streams are computed by need. Streams are computed as you need them. Even more significant, streams are computed incrementally. I'll come back to that point. So ladies and gentlemen, here's our lowercase thing. It's given us one word. One word. Before we asked for the lowercase, what did it give us? The. The only difference between this and this is that it performed the lowercase. Ladies and gentlemen, is it performing an entire map over the entire document to go from capital the to the lowercase? No, all it's doing is one operation on that particular word. Does it need to have the full document in memory at that time? No, it's doing it incrementally. It's changing that specific token, that specific word. It's mapping it. This is a big, big difference in terms of the amount of memory. It doesn't need to keep this gobs of memory around to represent the entire data structure, create another data structure for the next intermediate result, yet another. It's actually performing this whole series of computations, which looks so similar to what we saw with the array. It's actually performing that bit by bit by bit. And instead of creating big data structure to big data structure, it's just taking each data item in turn and frobbing it, taking it lowercase, checking if it's non-zero length, and processing it each one down the way until it needs more, until it needs a whole set. It needs to create a map of these things, in which case we'll start pulling more, until it needs to. But a lot of them can be just processed incrementally, step by step, by applying operations one by one. In short, and this is the key point, we're not performing full maps over this entire data structure. You might think by looking at this, here's a map here, here's a filter, there's a map to map it to lowercase, that we're going in multiple loops over this entire data structure. Gosh, I'm tempted to yell this. That is not true, ladies and gentlemen. It may look that way, and conceptually you can think of it that way if it is useful for you to conceptualize it that way. But for streams, that is not happening. It is not performing multiple maps over the data structure. Instead, it is getting each data item, performing an operation on that item, that one, successively mapping it, and then incorporating it to data structures on an as-needed basis. So we have replaced multiple loops over the entire data structure with incremental processing of each item. Do you get that point? Now, this is a modest pipeline. We've written it out all at once. It could be in many variables scattered through our program. But the point is that we have these successive maps that can be performed incrementally without creating gobs of data in memory, and without, in fact, needing to loop over the data structure many times. And that might have been a big concern when you see something like this. Wait, this is really wasteful. We're going through the entire data structure for the filter, entire data structure for flat map, entire data structure for map. Not true. For streams, it's not true. We're just performing the incremental processing one at a time. And if you're performing this on billions of data items, that makes a giant difference. You take each one at a time, process it successfully, save it away. Each one at a time, process it successfully, save it away. And you're saving just incomparable amounts of memory to if you're processing it all at once. So let's continue going back, unwrapping the onion. Here's filter not. So we got the. Get rid of the filter. What are we going to see?
Capital.
We're still going to see a the. Okay. Let's suppose we go back before the flat map. What are we going to see?
First sentence.
This is the first line of the document, ladies and gentlemen. That's what's being mapped here. So streams are different, ladies and gentlemen. The lazy nature totally transforms how we are actually performing the computation. And you want to get away from the kind of naive thinking that map means a full pass over the data structure. Filter means a full pass. Filter not. What? Flat map. These things are not true. We can actually do map. And rather than thinking of it that we're doing loops each time, changing something, we may be just taking each data item, updating it this way, taking its lowercase, mapping it to its length, taking its length, taking that length modulo something. The fact that we've put into multiple maps is almost immaterial in terms of the computation is just successively occurring on this data item. Yeah.
What are the implications for the group by statement? Because when you get the length of a certain collection, wouldn't it require everything?
Okay. So, and that's something I was hoping that could be brought out by emphasizing it earlier, but I appreciate you asking me about it so that it's very clear. So this is a nice idea that's occurring. This flat map, the filter, the map, all those can occur basically without looping. But what's occurring at this group by? Something special is occurring here. And Alan has put his finger, as normal, he's on top of something. What is special going on here?
I mean, they've computed all this stuff without computing. Seems like so, like because they've identified like there are like 5 strings and 10 and 14 without computing all the other stuff. That seems kind of
Yeah. Okay. So good. So good, ladies and gentlemen. In order to know that there's a 5 here, in order to know that there's a 21, something of length 21, something of length 29, something of length 34, what does it have to do? In order to give us the first value of this map, after the result of group by, that's a map coming out of this. In order to compute it, what does it need to do?
I guess they just find the first occurrence of a specific length and then just go. The rest of them they do not like store in memory, but the first occurrence they just compute the first occurrence.
Good. Okay. Yeah. So it has to know that there's at least one. Right? It finds the first A.
Yeah.
There's something of length 1. We'll remember that. And it hasn't yet explicated all of this, because why is this still a question mark?
There's more somewhere probably.
Well, yeah, it's a question mark because we haven't asked for them yet. And in fact, when are we going to ask for them? In this pipeline, when is this got to be boiled down from a question mark to something very concrete? If we look at the pipeline here, when does that end up being very concrete?
When we count them.
Yeah, when we count them. So it's going to be able to suffice to just have a question mark at this stage, but it needs to know how to find them. And this is a lot of what's going on behind the scenes. Just like there's computation going on behind the scenes to evaluate extra primes or extra fibs on an as-needed basis, what's also going on is that it has to be ready to be asked for further ones, ladies and gentlemen. It has to be ready to be asked for these further elements. So that if we say we want to know the size, it has to be ready to go get those and compute the size. And that's indeed what's going to happen right here. It's going to go compute the size. Yeah?
But it's checking every word for its size, right?
It is checking right now each word for the size so that it knows it's not a new size, and so that it knows where to get the words that will come in here for each of those. That's correct. That's correct. So it's got to be able to offer up all the words that will end up going here when we ask for its size. So it can count the number that are there. Right now it's a stream. It's not fully evaluated, but when we call it in, it will fill that in. And there's a lot of features like that. I'll tell you that within Scala, when we say something like filter not, it's actually a variant of this called filter with. And the idea is, ladies and gentlemen, that actually it will, even for something like array, it doesn't actually create a new data structure for filter with. What it will actually just remember is which were the indices that satisfied the filter. So if I perform a map over it, I don't have to actually create a whole new data structure. I just perform a map over just those indices and create a data structure from that. So it avoids creating a new data structure. But the point is that pipelines, some of it is going to be able to be performed incrementally. This flat map, absolutely. This filter, absolutely. The map, absolutely. But when we start to aggregate, when we start to compute things that depend on many items, like group by, it will need to actually go and go through a large number of previous ones. What would be another thing that would demand performing all the, going and performing a bunch of computations? Reduce, yeah. So let's try this here. Let's try val stream, or val, my simple stream here equals stream of 1, 2, 3, 4, 5. Okay. There's actually a from and 2 version of it that I could have done it more tersely. Okay, here's my simple stream, right? All it's computed is the first of them. But if I do my simple stream dot reduce and I add them together, what do you think I'll get? Okay, I'll get that, but if I do my simple stream again, what will I see? It has to compute all of them. By contrast, let's suppose I did my simple stream 2, and then I did my simple stream 2 dot scan of 0, and I did this. How many of them have to be computed for this? This scan is sort of doing the prefixes, okay? So only the first one is computed here. Now suppose I were to do scan dot take, the first 2 of these, right? Now let's see how many of them, have been computed, the first 2. So when it comes to aggregation, ladies and gentlemen, that forces us to get more items often, okay? We need to get more items. And so it's not magic. There's work to be done, but often in these pipelines, a whole series of operations can be performed incrementally in a way that avoids bringing things in large ways into memory. And for some systems that work with big data, such as Spark, this technique of performing incremental computation is front and center, part of the ways in which they secure economies of memory and the ability to operate in large bunches of data. Okay, so ladies and gentlemen, that's all we have time for today. In our next lecture, we're going to be taking this further and dealing with another aspect of these pipelines, which is troubling. Okay? And that is the fact that if we're dealing with a simple stream, for example, we're dealing with a stream that happens to be empty, and we want to perform, for example, a reduce on a stream that happens to be empty. We need to say, okay, A is an int here. Okay, A is an int, and we add, let's say, A and B is an int, and we were to add them together here. Okay, if we were to do this, we would get an error message. Why is this a problem? It's a problem because we might have a stream that starts non-empty, and we simply filter it by some criteria that makes it empty, and it will yield an error message in the middle of the computation. We'll see an extremely elegant way that we can avoid this and allow for building streams that are scalable and have principled error handling. So that's for next time. Thank you very much.